Hello everyone, today we'll be taking a look at the mole concept, redox and some stoichiometry for the GCE A-level syllabus. So before we dive into the content, it'll be good for us to take a look at some of the learning outcomes that we should know about in order to excel in the exams. As you can see from part A, B, as well as part D, we need to know some various terms which we will cover later, of course, as well as know how to apply some calculations. You should be quite familiar with this from your secondary school chemistry lessons, so today will be more of a recap rather than learning new content. So without further ado, let's dive in. So first off, let's explore the definition of relative atomic mass. The relative atomic mass is the ratio of the average mass of one atom of an element to 1/12 of the mass of an atom of carbon-12. You can find the relative atomic mass very easily in your periodic table. The relative atomic mass are the numbers below the elements. For example, you can see that the relative atomic mass of boron is 10.6 and that of carbon is 12.0 and so on and so forth. Next, we are moving on to the definition of an isotopic mass. So to recap, what is an isotope? Isotopes are two or more forms of the same element that have the same number of protons but different number of nucleons. For example, carbon-12 and 13. Carbon-12 has 6 protons and 6 neutrons. And as you may be able to deduce, carbon-13 would have 6 protons and 7 neutrons. As we can see, as stated in the definition, the number of protons are the same at 6, while the number of neutrons differs by 1. It is worth noting that the number following the element is the sum of the total number of protons and neutrons. Thus, the isotopic mass is the average mass of all the specific isotopes of an element. Now moving on to molecular mass. It's the mass of a given molecule, and how you derive it is calculating the sum of all the relative atomic masses of all atoms in a particular molecule. So for example, for CH4, which is methane, we have C, which has a relative atomic mass of 12, and 4 hydrogen, which each have a relative atomic mass of 1. So 12 plus 4 times 1 will give us 16. Next, we'll be looking at empirical and molecular formulas. So basically, the empirical formula of a chemical compound is the simplest whole number ratio of atoms present in a compound, while the molecular formula of a chemical compound is representative of the total number of individual atoms present in a molecule of a compound. So here we'll be doing a little practice. Please pause the video and take the time to calculate the empirical formula for each of these molecular formulas. Okay, welcome back. So first we'll look at glucose, which is C6H12O6. Now, as we previously mentioned, since the empirical formula is the simplest whole number ratio, we observe that these numbers can each be divided by 6. Thus, the empirical formula of glucose would be CH2O. Similarly, for butene, C4H8, we observe that the numbers can each be divided by 4. Thus, the empirical formula of butene would be CH2. However, when it comes to propane, we realize that we cannot do such a thing, as these numbers have no common factors. Dividing each number by 3 would not work, since 8/3 is not a whole number, and thus there is no empirical formula. So, the formula mass is the sum of the relative atomic mass of all the atoms in the empirical formula of a compound. So, as we have seen just now, glucose has an empirical formula of CH2O. Therefore, the formula mass would be 12 for carbon, 2 times 1 for 2 hydrogens, and 16 for 1 oxygen, which would give us 30. So, let's look at the difference between obtaining molecular mass and formula mass. For the molecular mass, we need to look at the molecular formula, while for the formula mass, we need to look at the empirical formula. In examinations, we are mostly concerned with molecular mass. It is very rare that we look at formula mass, but I believe it is still worth knowing. Moving on to more definitions, which you would definitely have encountered in secondary school, the mole and the Avogadro constant. As seen in part B of the learning outcomes. We have finished covering part A and part D. The mole is an SI unit used to measure the amount of any substance. 1 mole is 6.02 times 10 to the power of 23 particles, and the unit is mole, the short form. For the Avogadro constant, it is the number of particles in 1 mole of any substance. Its value is 6.02 times 10 to the power of 23 per mole. So let's look at how we calculate number of moles. So the relative atomic mass of an element as shown in the data booklet, which are any of these numbers below the elements, they are exactly the mass of 1 mole. Therefore, if we have x grams of a substance, to calculate the number of moles present, simply take the number of grams of the substance you have divided by the relative atomic mass. So for example, if I have 24 grams of carbon, and I know that the relative atomic mass of carbon is 12, 24 divided by 12 is 2, so I have 2 moles of carbon. So, balancing equations, which again you would have done in secondary school. An equation involves both reactants and products. As we know, reactants are written on the left-hand side, while products are written on the right-hand side. There must be the same number of each atom for each element on both sides of the equation. For example, Al2Cl6 will decompose to give us 2 moles of aluminum chloride. As you can observe, there are 2 Al atoms and 6 Cl atoms on both the left and right hand side. So this is balanced. And in the case of Al2Cl6, we have 1 mole of it, but we do not need to write 1 since the 1 is implied. So we'll just leave it with no coefficient. So how to balance equations? So firstly, we definitely need to identify all the relevant reactants and products and write them down first. We do not need to worry if there are a different number of atoms of each element on either side yet, since this is just the beginning. Then next, we need to make a note of how many atoms of each element there are on each side of the equation. This can be done as rough working at the side of the paper. So once we have determined how many atoms of each element there are on both sides, we need to see which are different, and we try and add numbers in front of each compound, so like the number of atoms of element is the same on both sides. More cases than not, this involves trial and error, so there's no need to be worried if you don't get it as quickly as you like. However, one tip to make it a bit easier would be to balance hydrogen and oxygen atoms last, since these are the most common. Okay, please pause the video now to take a look at this example and try and apply the tips that we previously mentioned to help you solve it. Okay, welcome back. So as we can see here, we have NaOH, H2SO4, Na2SO4 and H2O. Since we mentioned that hydrogen and oxygen should be balanced last, now we first need to look at Na as well as S. We observe that there is 1 Na and 1 S on the left hand side and 2 Na and 1 S on the right hand side. Since the number of S atoms are the same, we balance Na. So if I have 1 Na here and 2 Na here, naturally I would put 2 as the coefficient of NaOH. Now since the number of Na and S are the same and all we are left with hydrogen and oxygen, let us balance them. We have 2 oxygen from NaOH as well as 4 oxygen from H2SO4. Thus on the left side we have 6 oxygen atoms. Then on the left hand side we have 2 hydrogen from NaOH and 2 hydrogen from H2SO4. So we have 6 oxygen and 4 hydrogen on the left hand side. On the right hand side, we currently have 4 oxygen from Na2SO4. And we know since that there are 2 Na on both sides, the coefficient here must be 1. right? So if we have 4 oxygen here, but 6 oxygen here, then naturally it follows that we would need two oxygen here, right? So the coefficient needs to be 2. Then we double check again. There's 4 hydrogen here, and there needs to be 4 hydrogen here. So if the coefficient is 2, then there will be 4 hydrogen. So this is very good for us. So this would be the fully balanced equation. If you are still a bit unsure or unconfident about how to balance an equation, there are many good resources and practices online for you to further develop your skills. Now we move on to redox, or rather a recap of redox. So redox is basically a type of chemical reaction in which oxidation states of atoms are changed. And a redox reaction needs both oxidation and reduction. Here's a small table to help you recap the differences. Oxidation involves an increase in oxidation number, while reduction involves a decrease in oxidation number. Oxidation involves loss of electrons, while reduction involves gain of electrons. In oxidation, as the name applies, there can be gain of oxygen, while in reduction there is loss of oxygen. Or there can also be loss of hydrogen in oxidation, while in reduction there is gain of hydrogen. Hopefully these are more familiar to you now, if they weren't before. One easy way to remember things about redox is the term oil rig, where oxidation is loss of electrons and reduction is gain of electrons. So in redox there are half equations. There are reduction half equations and oxidation half equations. As we previously mentioned, in reduction, electrons are gained, therefore they are written on the left hand side. Or in oxidation, since electrons are lost, we write them on the right hand side. So as the name implies, since there are two half equations, we can combine them into a full equation. However, there must be one oxidation half equation and one reduction half equation. There cannot be two oxidation or two reduction half equations. So one important thing to note about this combination of half equations is the number of electrons must be the same for both half equations, as the number of electrons lost and the number of electrons gained are the same. Then when you combine them, the reactants of each half equation are added together, and the products of each half equation are added together. Keep this in mind for now. We will explore this in further detail later. Okay, so let's attempt a sample question from the 2018 A-level paper. It says when iodine is oxidized by nitric acid, a white crystalline solid oxide can be isolated from the mixture. 0.001 moles of this oxide reacts with 0.01 moles of acidified potassium iodide to give 0.006 moles of iodine, I2. What is the oxidation number of iodine in the oxide? If you like, please pause the video for a moment to try and solve this. This is quite difficult, so don't be too frustrated if you can't get it. Okay, welcome back. So firstly, our first step is to write the equation so that we can better understand what is going on in this process. We need to identify relevant reactants and products to do this, as well as identify the mole ratios. So basically, we can observe that there are different moles of substances used. So to make the simplest way to create a mole ratio is to create like a whole number ratio. So as you can see here, 0.001 is to 0.01 is to 0.006 is 1 is to 10 is to 6, right? So based on this information here, we know that there is 1 mole of unknown oxide that reacts with 10 moles of I- to produce 6 moles of I2. Take note here that even though it mentions that acidified potassium iodide is added, we do not need to include it, as only the iodide ion is relevant in the equation. So now we need to balance the equation. We observe on the right hand side there are 12 iodine ions consisting of 6 times 2, while on the left hand side we have 10 I minus than the iodine from the unknown oxide. Therefore, we can conclude that the unknown oxide has 2 iodine atoms since both sides must have 12 iodine. Next, we need to identify the oxidation number of the iodine atoms in each substance. For the unknown oxide, we have yet to determine it, but in the iodine ion, the iodide ion, the oxidation number is -1, while in iodine the oxidation number is 0. So we can observe that the iodine with an oxidation of number of -1 eventually became iodine with an oxidation number of 0, right? So we can deduce that 10 I minus ions each lost 1 electron to increase their oxidation number from -1 to 0. Going back, since there is an increase in oxidation number, that means that they were oxidized, and thus they lost electrons. Yeah, so since a total of 10 electrons were lost, and we know that the number of electrons lost needs to be the same as the number of electrons gained, 10 electrons need to be gained from the 2 iodine atoms in the unknown oxide, right? And since electrons need to be gained, we can deduce that the iodine atoms in the unknown oxide have to be reduced and have a decreased oxidation number, as stated here. Thus, 1 iodine atom in the oxide needs to gain 5 electrons to reach an oxidation number of 0. And since we need to gain 5 electrons to reach an oxidation number of 0, it means that the oxidation number is +5. Since each electron is negative, so 5 electrons will be -5, and +5 minus 5 would give us 0. Thus, the answer is B. Please feel free to review this again if you are confused. Let us now look at another 2020 A-level question. It says 1.00 grams of boron carbide completely oxidizes to form 2.50 grams of boron oxide, B2O3, and 0.80 grams of carbon dioxide. What is the empirical formula of boron carbide? Please pause again if you would like to attempt this question. Okay, welcome back. So, step 1, we need to identify the molecular mass of new compounds. So for B2O3, it would be 2 times 10.8 for boron and 3 times 12.0 for carbon, which would give us a total of 69.6. Then for carbon dioxide, it would be 12 for carbon plus 2 times 16 for the 2 oxygen atoms, which would give us 44. Then we need to calculate the number of moles of each compound. So since we have 2.50 grams of B2O3, we eventually get 0.0359 moles. While for carbon dioxide, since we have 0.80 grams of it, we get 0.0182. So in step 3, we come up with an equation of the information gathered. We do this by calculating whole number ratios of the moles, as mentioned previously. So we can do this by taking the mole with the larger number divided by the mole with the smaller number. In this case, there is more of B2O3, which is 0.0359, as compared to CO2, which is 0.0182. So after you divide it, you find it out is approximately 2. Therefore, we can say there is approximately 2 times as much B2O3 than CO2. Right, so these are the products, 2 moles of B2O3 and CO2. Then we have an unknown amount of boron carbide and oxygen. Right. So we can, since we know that boron carbide only has boron and carbon, we calculate the number of boron and carbon atoms on the right hand side. So the number of B atoms in 2 moles of B2O3 would be 2 times 2, while the number of carbon atoms in CO2 is 1. Thus, boron carbide only containing boron and carbon would be B4C, and thus the answer would be D. Okay, another 2019 A-level question. Soda glass is composed of 16% of boron oxide, B2O3 by mass, and 84% lead oxide, PbO by mass. What is the Pb to B molar ratio in soda glass? This question actually helps us cover part E of the learning outcomes. So far we have covered A, B, D and F. Okay, so to do such questions where they tell you the percentage composition, the first and easiest step is to assume we have 100 grams of the compound. Since we have 100 grams and the total percentage is based out of 100, we can easily calculate the mass of each substance. So here, since we have 16% of B2O3 and 84% of PBO, we have 16 grams of B2O3 and 84 grams of PBO. Next, we calculate the molecular mass of compounds as shown previously. We just refer to the data booklet and add them all up. So for B2O3 it's 69.6 and PBO it's 223.2. Then we calculate the number of moles. Again, it is the mass of the substances we have divided by the molecular mass as determined from the data booklet. So for B2O3 we have 0.23 moles, while for PBO we have 0.376 moles. So finally, to calculate the number of moles of required atoms, we observe that in the question they asked for the PB is to B ratio, but they give us B2O3 and PBO. So as we can see, 1 mole of B2O3 has 2 moles of B, as seen from the 2 beside the B, while 1 mole of PBO has 1 mole of PB. Therefore, the PB is to B molar ratio would be 0.376 as shown here, followed by 2 times 0.230. 0.230 is the number of moles of B2O3, which is 0.817, which is approximately 0.82. Thus, option A is correct. A small mini conclusion we can make from looking at these questions are the calculation of molecular mass and moles is very important, and we need to understand how to use mole ratios. Furthermore, the differences between compounds and atoms should be taken note of. Atoms make up compounds, so 1 mole of compounds has more than 1 mole of atoms. Again, 1 mole of B2O3 has 2 moles of B and 3 moles of oxygen, while 1 mole of PBO has 1 mole of PB and 1 mole of oxygen. Okay, yet another exam question. This will cover part C of the learning outcomes. So it says a sample of silicon contains 3 naturally occurring isotopes, 28 Si, 29 Si, and 30 Si. The sample is made up of 92.23% 28 Si, and the relative atomic mass of silicon in this sample is 28.10. So based on this, what is the percentage of the isotope 29 Si in the sample? So in order to do these questions, we need to be familiar with the formula to calculate the relative atomic mass of the element. To calculate it, we need to take the percentage of isotope A times the mass of isotope A plus the percentage of isotope B times mass of isotope B, and so on and so forth, depending on how many isotopes the question gives you, divided by the sum of all the percentages of the isotopes. So in this case, we see that the relative atomic mass of silicon is 28.10. So 28.10 is 92.23% times 28 plus the percentage of 29 Si times 29 plus the percentage of 30 Si times 30 divided by the sum of all the percentages, which would be 100. So we can solve this by trial and error. So we basically choose the options of the given in the MCQ question one by one. Then we can use it to calculate the percentage of 30 Si by using 100 minus 92.23% minus the percentage of 29 Si we chose. Then we substitute these two values into the unknown percentages to check if it gives us 28.10. In this case, the answer is A, and we can simply check it by inputting the necessary values into the calculator. Okay, now by doing some of the questions, we have sort of covered part G and part H of the learning outcomes. But to further solidify our understanding of part G and part H, let us take a look at a more complex question from the 2020 A-level paper. So this is the information that is presented to you. Please take a while to read it. I have written some notes in the middle because in order to get them, you need to know content from the syllabus that is taught much later, so we do not need to worry about that too much for now. Just try and make use of what has been covered in this video to help you answer the questions to the best of your ability. Okay, right, so firstly, we notice that there are two half equations here, right? As we can see, the uppermost equation has the electrons on the right hand side, and the bottom equation has the electrons on the left hand side. So this means that the upper half equation is oxidation, while the bottom half equation is redox. Because in oxidation, you lose electrons, thus they are on the right hand side, while in reduction you gain electrons, thus they are on the left hand side. As mentioned earlier, in order to combine them, we need to make the number of electrons the same. So we can do this by identifying the lowest common multiple of 2 and 5, which is 10. So we multiply the upper half equation by 5 and the bottom half equation by 2. So you will get these two equations over here. Right? Then when you combine them together, you add all the reactants together and all the products together. So you will get this long list. But we are not done yet, because as we can see, there are some common terms. For example, we have 5H2O on the left and 8H2O on the right, and 16H plus on the left and 10H plus on the right, as well as 10 electrons on both sides. Thus, we can cancel them off. Thus, our final equation will look something like this. Next, for step 2, as we previously mentioned, we need to knowing how to calculate the number of moles is critical in doing such questions. The number of moles used is the concentration of a solution times its volume. Both should be calculated in dm³. However, they mention here that the acidified MnO4- ions are added in excess. This means that we cannot be sure exactly how much has been used in this equation. However, what we do know is the number of moles that have been added. Sorry, typo. So, as mentioned, concentration times volume will give us the number of moles. Right, then based on the question, we can calculate the amount of Na2S2O3 used. So, once again, concentration times volume will give us number of moles. And we observe here that for every 2 moles of S2O3 2- that react, 1 mole of I2- reacts. So, you might find it weird that they put it as S2O3 2- when we have Na2S2O3, but there's no need to worry because 1 mole of Na2S2O3 has 1 mole of S2O3 2-. So the number of moles of Na2S2O3 will be the same as the number of moles of S2O3 2-, which is 0.000336. So since the mole ratio of S2O3 2- to I2 is 2:1, there is 0.000168 moles of I2 that reacted. So this means that 0.000168 mole of I2 was produced from reaction of MnO4- and iodide. We know that for every 2 moles of MnO4- reacted, 5 moles of I2 are produced. Thus, the amount of MnO4- that reacted is 2/5 times 0.000168 equals to 0.0000672 moles. And initially we had 0.00025 moles of MnO4-. But now we only have 0.0000672. Thus, we can calculate the amount that was reacted in the full equation that we obtained earlier. Then we observe that for every 5 moles of NO2- that has reacted, 2 moles of MnO4- reacts with it. Thus, we calculate that the amount of NO2- that reacted is 5/2 times the amount of MnO4- that reacted, which gives us 0.000457 moles. Since 1 mole of NaNO2 contains 1 mole of NO2- ions, that means the amount of NaNO2 is the same at 0.000457. Then, knowing how much NaNO2 we have in moles, we can calculate its mass in grams. Simply take mole times the molecular mass, as can be determined from the data booklet, which gives us 0.031533. And since we know that there is 0.031533 grams of NaNO2 in 1 gram of sample, the percentage by mass is 3.15%. I hope this video has been a good recap of some of the things we need to take note about mole concepts, redox, and stoichiometry in GCE for the A levels. I plan on producing more videos in the time to come to offer you some tips or instructive content to better help you with your chemistry. At the same time, I would really appreciate it if you let me know what you would like to see, or what I did not explain well and you would like me to explain again, or really just any other feedback you have. Thank you so much for watching, and I'll see you soon. Bye bye.